In assignment 45, we're going to learn something called summation notation. It's not super hard, it's just a new notation of how to write a sum of a list of numbers in a shorter way. So it says, much of our work in this unit will concern adding the terms of a sequence. In order to specify this addition or summarize it, we use a new notation known as summation or sigma notation that will represent these sums. This notation will be used later in the course, and actually not this year, later in the course, because we're kind of skipping that part of the course, but it's used in statistics in a lot of different ways. So this looks like a super complicated definition. Basically, when we are finding this notation, when we see that notation, and we see something that comes after it, like a function, we are going to plug different numbers into this function, starting with whatever value is at the bottom, so A, and basically counting up to whatever number is at the top. So we plug in, like, let's say we were starting with a 2, we would plug in 2, 3, 4, and we would continue. Let's say we had an 8 on the top for n, we would plug in until we plugged in 8. I is called the index variable, which starts at the value of a and ends at the value of n and moves by unit increments, increasing by 1 each time. So this is not I like the imaginary I, but since I goes with the word index, we see that we're using the letter I. So that's a little tricky whenever we use the same letter or variable for two different things, but this is not I as in the imaginary I. So let's look at our first example. Once you start to see them, it's actually pretty easy, as long as you recognize what to do. So here is our expression, 2i to the negative 1. And on my summation notation, it looks like I'm going to start by plugging in a 3, and I'm going to plug in numbers up to 5. So the first thing we are going to plug in for I is a 3. And then we're going to plug in a 4, and actually rating them this way is kind of nice, basically writing them vertically. So we're going to get answers for each of these. So I started with plugging in a 3 and counted up till I got up to 5. So I don't have a great spacing here, but this is 2/3, because 3 to the negative 1 means divide by 3. This one is 2/4 or 1/2. I'm just going to rewrite that as 1/2. And this one is 2/5. Now this is summation notation, so once I get those answers, I basically just add them up. So that's something I could do on a calculator. Basically, if I added those up, I found an LCD, I would end up with 47/30 as my answer. So this is my final answer, that sum. These numbers I added together, I know I put a box around them to show what I was adding, but that's not my answer, it's the actual sum. So we'll look at another one. Basically on this one, instead of having an I have a K. You can really have whatever variable you want there, down at the bottom. So this K value starts out at -1 and goes up to 3. And I'm just doing K squared. So I have -1 squared, 0 squared, 1 squared, 2 squared, and then the last number I'm going to plug in, that number up top, is a 3. So we get each of our answers. So -1 squared is 1, 0, and 1, and 4, and 9. And then since this is a summation, I'm going to add those values together to get my final answer. So looking at those values, if I added them up, I would get 15. So I would suggest pausing the video and trying the next 3. I will quickly go over them once you're done, but just to make sure you have the gist of what's going on. Okay, so looking at letter C, I need to plug in a 1 through a 5. So this is 1 minus 1, 2 minus 1. Now the variable I'm using is J. And up to 5. So we'll get each of these answers and then we'll add them together. So remember, we want to still follow PEMDAS. We're not going to do 3 times 2. We're going to do 2 to the 0, for example, on the first one first, and then multiply by 3. So my answers I get are 3, 6, 12, 24, and 48. And those add up to 93. Looking at our last two, this one's going to be an interesting pattern for D because basically I'm raising -1 to different powers. If we think about that, we'll get -1 sometimes as the answer and 1 sometimes, depending on if the exponent is even or odd. So once again, start with plugging in 1, end with plugging in 5 for I. So -1 to the first is -1, -1 squared is +1, and we're basically going to alternate like that. So if I add these up, basically the -1s and 1s will cancel, except we have one -1 left. So I'm going to write the sum over here. So the sum of all of these is -1. And our last one, let me just cut this off. We're plugging in a 1 to a 4. So this is 1 plus 2 times 0 is 1, 1 plus 2 times 1, 1 plus 2 is 3. And just like everything else with sequences, sometimes we see a pattern and we can finish that pattern. So the sum of these numbers is 16. I am actually in a room without a graphing calculator on my computer. So in this video, I can't show how to do this on a calculator. I'm probably going to make a separate video for how to do this on the calculator, but there is a way to check these. On a test, if you're showing work, you'll have to write this work out, but you can actually type these directly in the calculator and they will give you these same answers. So as I said, look for another video attached. I would definitely watch that one if you missed the lesson. Which of the following represents this expression? I'm just going to erase a little bit so I can read it. So this is just the same deal. We're starting out by plugging in a 1 up to a 4. So we have just showing you could write it horizontally. So I plugged in a 1, plugged in a 2, plugged in a 3, and plugged in a 4. And if I add those up, my LCD is 12 for 1, 2, 3, and 4. And changing my numerators, I would end up with 25 over 12. So that's your basic summation notation, plugging in numbers and adding up their results. And now we're going to look at a couple, start to think about how do we tell which summation notation represents that, and also writing our own summation notation. Exercise 4 also starts to incorporate a little bit of recursion. We'll talk about that in a second too. So this one says, which of the following represents the sum? 3 plus 8 plus 15 plus 24, following this pattern up to 80. So in order to check these, we want to actually start to write out some terms and see if they match up. So for example, and I'm actually going to plug in and find one value for each of them first. So here, the first thing I would plug into number 1 is a 1. Okay, so I plugged in my 1, and this evaluates to 3 plus 5 times 0 is 3. So that's a possibility because I want my first number to be 3. I'm going to do the same for the next couple. So number 3, I have 1 squared minus 1, which is 0. So that can't be the answer because I need my first term that I'm adding to be a 3. So it's definitely not that. Over here, I have 2 squared minus 1, which does end up being a 3. So that's a possibility. And then my last one, I just have a 3. So that's also a possibility. So far, plugging in the first number, I've only eliminated choice 3. Now I'm going to plug in my second number. So here I plugged in a 1. Now we're going to plug in a 2. So this is 3 plus 5, which does equal 8. So that one's still looking good. Here I need to plug in a 3. So 3 squared minus 1 equals 8. So that also looks good. And then number 4, I'm just plugging in a 4 now, right? Because we started with 3, now I'm plugging in a 4. So I got a 3 and a 4. So this one's not right because I need my second term to be 8. Okay, so let's go on to the next number. So in this one, my next thing I'm plugging in, I plugged in a 1, I plugged in a 2, now I'm going to plug in a 3. So 3 plus 5 times 3 minus 1, that's going to give me 3 plus 5 times 2, which is 13. So this one does not look so good because I want my third term to be 15. Over here, I have plug in a 2, plug in a 3, plug in a 4, and that equals 15. So this one looks good. Just to make sure I didn't make a mistake, usually what I'll do is I'll plug in the last number and make sure it matches up with that once I'm down to my final one. So 9 squared minus 1 does equal 80. So I'm pretty sure based on process of elimination and then checking the end that 2 is the answer. So our last question on this video, I'm going to do exercise 5 and 6 on a different video, is just a little look at recursion and connecting recursive definition to a summation. Now this is an extension question, but it is good to look at. So here it says I want to add up this expression plugging in a 4 through a 7. So what that means is I want to add a sub 4 to a sub 5 to a sub 6 to a sub 7. Now we know that this denotes terms in a sequence. It's not like a sub 4 is a number. It's like not like a times 4 or anything like that. So I need to go over to this definition and find out what those numbers are. So it looks like my definition says that I am going to need to start with 2 terms. And to get the next term, I'm going to add the last term to twice the term that came before it. So to find a sub 3, which is next, my sequence starts out with 0, 1, right? I'm going to add a sub 2, because if this is a 3, that's a 2, to 2 times a sub 1. Just going to move this out of the way. So a sub 1 or a sub 2 is 1, right? So I'm plugging in a 1 here, plus 2, a sub 1 is 0. So that also equals 1. So I'm going to write one more time. I'm going to write that whole thing out. So to find a sub 4, I'm taking the term before it and adding it to twice the term before that. So a sub 3 is 1. And then we're doing 2 times a sub 2, and a sub 2 is also 1. So this equals, equal sign there, equals 3. So kind of going a little faster with this, to find a sub 5, I'm adding a sub 4, which is 3, to 2 times a sub 3, which is 1. So that gives me 5. A sub 6, I'm adding a sub 5 to 2 times a sub 4. So that's 5 plus 6 is 11. And then our last one we need to add up, right? If I look back over here, right, this is what we're adding up. To find a sub 7, which is going to have to move down into this question, I'm taking a sub 6 plus 2 times a sub 5. So that's 21. So what am I adding up here? I'm adding up a sub 4, a sub 5, a sub 6, and a sub 7. So that's 3 plus 5 plus 11 plus 21. So if I add those numbers up, that gives me 40. So as I said, nothing new in that problem, but it's connecting that you could also use a sequence definition, like a recursive definition, and use that to be applied to something with summation notation.